And up to now, we saw linear transformation as a parallel. But we know that a linear transformation is a matrix. True? Now we are going to understand how actually a matrix is an opportune representation under a certain specific viewpoint of a linear transformation. And actually, a linear transformation is much more than a matrix. A linear transformation is a collection of matrices. We are going to see it. So, this is the picture of a linear transformation. Are we together? You see, the origin goes into the origin, and parallel lines stay parallel lines. Are we together, people? 1, 2, 3. And this one is also in R3, R4, R4 to R2, R1 to R7, etc., etc., etc. Drawing, people, I'm constrained to use R2 and R2, but it's generic. Okay. And I might also have done something like this. I would have gotten something slightly different too. The physical stretching of space is defined by A. A is not defined by the lines. A is defined by how, starting in a certain way, I will end up in a certain way. Are we together? Do you see the physical stretching? I do a physical stretching, means that if I was choosing those ones, I would go this one. But the same stretching, if I was choosing those ones, I would go to something else. Together? If I was choosing those ones, I would get into those ones. True? If I was choosing those ones, I would get into those ones. True? If I was choosing those ones, I would get into, let me think a little bit, those ones. Together? The physical stretching is something. As soon as I select a certain set of parallel lines, I will end up into parallel lines. But the stretching is not defined by which parallel lines that I'm choosing. Are we together on this? The stretching is something. What I choose to represent is what I choose to represent. This is a hat or cappello or lua. Is it a lua? Yeah. It's the same physical object independently of how I'm calling it. How much are we together, people, on this stuff? Now, how do I represent this transformation from a domain to the codomain? As a matrix. Let's take any object in the domain, any vector in the domain. Okay, you take one. This one will be mapped in somewhere. True? This one gets mapped here. True? Perfect. And then I take another one in the domain, and I will go somewhere else. True? And I might have chosen something different here, I would have gotten something different here. I might have chosen something different here, I would have gotten something different here. True? Depending on what I choose here, I will get something there. And in a certain sense, the transformation is not defined by what I choose, but somehow by how the transformation is. Okay? Essential point, this second object that I take is not going to be parallel to the first object. Okay? Are we together up to now? Perfect. Now, this is the case R2, for which I've got two elements in the domain. If I was R3, this would be a blob, three-dimensional blob. I might choose another one, not in the plane. True? If I was R4, I could choose another one, not in the space. Are we together? And of course, if I've got Rn, I might choose n here, and I will end up with n objects. True? Here, I'm choosing them, so to form what? A basis. Okay? So the stuff that I choose, and I choose arbitrarily, as I want. I choose a basis. And then I will be transformed. Every element, let's go back to R2. Now, you've got to imagine that here I will choose n. I plot 2 because I've got R2, but it will be n. How much are we together on this? I'm stressing it out because it's something that sometimes makes some confusion. Question. Essential. I need a basis. Essential. Essential, not important. If you don't choose a basis, everything breaks down. Okay? Perfect. So, we choose a basis in the domain. That means that the stuff is not linearly dependent. Are we together, people? 1, 2, 3. We are talking the same language, true? If I start from a basis of a domain and I end up here, the stuff that I get, am I guaranteed that they are linearly independent? Yes? No? I do not know. Discuss. Is the question clear? If I start from a basis, I start here with stuff that is not aligned. And I will end up with something, and the definition is like the A will define me in a certain way. The stuff that I get here, how many, if I start with n objects here, how many objects do I get here? N, true? Those n objects, are they going to be linearly independent? Yes, no, I do not know. Discuss. So, people, what would you say? What would you say? I would like everybody to answer. 3 is very important for me. I would like everybody to answer. No? Why? Let's make a very immediate example. If I've got a domain that is R3, how many objects am I going to choose? 3, true? 1, 2, 3. Or even easier, E1, E2, E3, true? Together is the canonical basis stuff. How many objects will I get here? 3, true? I start with 3. I make 3 transformations. I will end up with 3 stuff. Can 3 things in R2 be linearly independent? No. And if the transformation is even worse, if the transformation is that everything here gets mapped into a line, the 3 stuff, where do they end up? They end up one here, one here, one here, true? Even worse, true? And also if I was starting with 2 dimensions and I was going from R2 to R2 and I was having this whole plane was stretched into a line, also in this case, I wouldn't have, true? So it's not guaranteed that starting from linearly independent, I end up in linearly independent. Sometimes it might happen, but it's not guaranteed. very much together, kind of together, not at all together. If you have questions, people interrupt me. Question. Sorry? So I restate, before the solution is, I am not guaranteed that starting from linearly independent, I end up with linearly independent. Okay. It might happen, but you are not guaranteed that it's always going to happen. Sometimes it does, sometimes it doesn't. Okay. Now, we selected a basis in the domain. Okay. The basis in the domain gets transformed into something in the codomain. Is that something in the codomain the basis? No, it's not guaranteed. True? We saw that they might not be linearly independent. True? We might also have deficiency in the sense that the amount of stuff that I get is not enough for making a basis. In which case, think and discuss about which case. In which case, I have that the mapped objects is not sufficient to form a base in the sense that there's some that are missing. Is the question clear? I'm giving here an example. People, are you seeing the example? Here I start with R2 and then end up in R3. In R3, how many objects do I need to have a basis? 3 objects. How many objects do I start with? 2. Okay? So I start from a basis. I will transform it. The stuff that I get is not guaranteed at all to be a basis. How much are we together? Excellent. At this point, what do? I choose a basis here. I choose the one that I want. True? Now, what is the matrix? The matrix is going to be expressing each of those ones in terms of the codomain basis. The matrix A, that is the numbers that we get, is going to be those numbers with respect to this basis here. And now we see it from a formal perspective. So, essentially, the operation for making the physical transformation, capital A, or that calligraphic A, is always going to define the physical stretching. Capital A is going to define the numbers that characterize these. Okay? So this is the object, this is the name of the object. Together, the name of the object is something that depends on this operation. And now we are going to see the numbers, but now we are going to see first from a conceptual perspective. I have to define a basis in the domain. I have to define a basis in the codomain. I have to transform the elements and then express what I got in terms of those bases. Define something, a basis here, define a basis here, transform, express those ones in terms of those ones. And then the numbers follow. The name, capital A, of the object calligraphic A is, depending on the choices of language that I use, the name will follow. How much are we together up to now? We didn't see the numbers, now we are going to see the numbers. But the procedure, is it clear? Yes, no? Yes, at all, not at all. Okay, let's see the numbers then. Now we do it numerically. I take elements in the domain. Now I'm making an example with R3 just to mess up a little bit with the intuitions before, to the graphical representations before, so that hopefully with these three-dimensional examples, things are going to be more clear. Together that we chose a basis, okay? So they are a basis here. I choose the other basis. You see, generic. Perfect. Edge. Mona Lisa. So my basis, if this one is my 0, my basis might be left eye and right eye. Together? Okay? So this one and this one are objects in the fabric of space that is before transforming the fabric of space. Are we together? Then I take the Mona Lisa and I transform it. Let's pretend that this is a linear transformation of the Mona Lisa. I might choose as a basis this one. Perfect. This one is perfect. I might choose the tip of the nose and this piece of grass as the basis of the codomain. Are we together? Are we seeing it? And I can do this choice in an arbitrary way as soon as this one and this one are basis of where I start and basis of where I am. Are we together? Perfect. What can I do then? Well, V1 gets transformed into an object. True? This object here is going to be a V1. Let's call it this one. This one is my calligraphic A V1 in the domain. And then this point here is going to be what? Actually, since this is a basis, I can express this point in the coordinates defined by this basis. True? That is this. Are we seeing that this one is, those coordinates are essentially the expression of this point in terms of this basis. How much do you see it? 1, 2, 3. Those are objects. This is an object. This is a number. True? Or better number, a vector. Let's make it. And now you tell me. This point here. This one. This one. Under this basis. Which coordinate does it have? You find them. Approximate. It's going to be, the drawing should be kind of clear. Minus 1 V1C, 0.5 V2C. People, are we together? Shall we do another one? This point here, which coordinate does it have? Go, you go. Discuss. First coordinate, 0. Second coordinate, minus 1, minus 1, minus 1. Are we together, people? 1, 2, 3. So something. Let's do it. This is the ingredients of a recipe. Those are how much you use each ingredient. True? Together? Perfect. If I take this one and I transform it, I go here, it will have a certain coordinate system, or better, under this basis, it will be represented as a certain vector. Do we see it? Perfect. And then, if I take this object here, that goes here, I don't know, here, it will have another vector. True? If I change this basis here, this vector here stays the same. Changes, I do not know. very much changes. True? Very much changes. If I change the language for which I express stuff in the codomain, my vector here, that is how much I combine the ingredients, will change. If this one goes here, and instead of using this basis, I use this basis here. Okay? What will happen to this vector here? Becomes half. Do we see it, people? 1, 2, 3. Excellent. If I was inverting the coordinates and putting this one first and this one second, what would happen to the coordinates? They would flip. Question. I didn't get it. Sorry, may you repeat? Mm-hmm. Let's do it numerically. This object here, let's pretend that this object here is the mapped stuff. Under this basis here, the coordinates are -1, 0.5. Together? Then I've got these other bases. The coordinates are going to be now -2, 1. -1, -2, 1. I could have been messing up. Okay. Are we together, people? Perfect. Now, the important point is this one. The physical transformation, does it depend on whether I choose those or those? The physical process, does it depend on how I call it? The physical stretching is the same. I should have put, I'm going to put it. Look at this situation here. Ignore the grids. The physical transformation, does it depend on which basis I use here and which basis I use here? No. True? Question. For each base, if we choose the first one, then the second one has only one option. Absolutely not. But isn't the process defined by how it changes the base? Yeah, but with two things. Let's go back here. Now, if I change this one, those ones change. True? If I change those ones, this one change. Yes, no, I do not know. Discuss. What would you say, people? I would like everybody to answer. People now, I see very, very few people answering, and I really need everybody because this part here is very conceptual. This is the basis of what we are going to do in this course about linear algebra, and this is essential for you to understand because otherwise the next control courses that are based on linear algebra, they are going to be based on something that is unclear. We need to be on the same page of the same book. Are we together on this? This is, believe me, people. This has to be extremely clear. Okay, let's make an example. Let's pretend, and then we will see that the answer, you will find the answer. Let's pretend that this one gets mapped into something for which whenever I map this one into the stuff and I select these ones, I get as coordinates -1, -2. Okay? Now, instead of using this basis here, I use this basis here. This one, and half. What is going to be this one? How does that one transform? I think it halves. So this one gets mapped here. Let's make it -1, -2. Okay, this one gets here. This one gets mapped where? Half of it, true? So it's going to be 0.5 -1. Minus 0.5 -1. Do you see it? Those numbers depend on three things: where I start, how I transform, where I end. Where I start means I choose a certain lingo to define the starting point. And I choose a certain lingo to define the endpoint. And then I have the physical transformation that disregards your languages. It's just taking the fabric of space and warping it in an according way. Those ones depend on domain basis, codomain basis, and physical transformation. How much are we together, people, on this? And then we take the question. Okay, question.
But as he was saying, I don't really understand, because with this method where we choose the basis for the first domain and for the codomain, like for the same transformation, by changing the second basin, we could have
basis. Sorry, I was interrupted.
We could have infinite kind of like matrices to represent the same transformation. Which means that we choose the basin.
This one is represented by a manifold of matrices. A linear transformation has infinite names. Depending on what you choose, it will have a specific name. How many languages are there in the world? Infinite languages in the world. How many different ways do I have to indicate this physical object that is a hat? Infinite number of names. True?
But if I choose the basin of the codomain, the transformation of the basin of the domain.
That will be a very specific choice. He's saying, but if I choose as a basis for the codomain the transformation of the basis of the domain, if you can do it, because not always you can do it, okay, then you will have a special name because you're choosing a special language. True? We are going to choose that language. Okay? But in general, now if we go on, these holds, true? This holds, true? If I put together all the stuff here that gets mapped and all the representations, I get a matrix. Are we together? Now, and then we finish, and then we take a pause, but let's finish it. If I start from a generic X in the domain, this one, what is it going to be? This one is represented as a certain vector. This one might be 0.5, 0.7, 0.7 plus 2. You see it? So this one might be 0.7, 0.5, 2.3. Are we together? That this one here, that is the vector that you use to indicate the generic point X, is actually something that is, depending on the language that I choose, it will have a certain vector. Are we together on this? But then, if I want to transform this object, how do I do? This object here is the basis and the language under the basis. But then it's a linear transformation, true? It means that I can take these ones and transform them, and I get into these ones. True? But then those ones are going to be what? Name in the codomain matrix. So what do I have? Ax is equal to y. How does this read? It's vector in the domain, transformation of the basis in the domain into the codomain. This is our A, true? This is our A. This is our A, true? You see how our A depends on basis in the domain, basis in the codomain, the transformation. How much are we together, people? If I choose this basis and this basis, I will get a specific A. If I choose this basis and this basis, I will get a specific A. The physical transformation is the same. Okay? Together? Shall we take a pause?